Welcome to Los Angeles. I hope everyone's very excited about the technologies that we all heard about in the keynote. And you may be curious about why I'm showing you Quake 2. Do we have any gamers out here in the audience? Anybody used to play Quake 2? Fair number of people. This looks like pretty decent performance, right? Not seeing any choppiness, no lag. You might be surprised to hear that this Quake 2 binary and all the DLLs that are in the Quake 2 directory that it uses are compiled into MSIL, and they're running on top of the JIT compiler and on top of the CLR. Now, this was done using the CLR interop technologies that are available through the Visual C++ product. The reason why this is important is because once that you've got your application like this, you can do other interesting things. For example, if I start a game here, and I am an id software programmer, and I want to extend my application using some of these cool new .NET features that I've heard about, or now some of these WinFX features on the Longhorn timeframe, I'm going to run this extension called Radar that Vertigo Software wrote. This is a WinForm that pops up. This is all done using the .NET drawing APIs, and you'll see some blocks and circles here. The circles are just features, things like canisters. The red dots are enemies and the green dots are power-ups. This isn't too interesting though. So what happens if I click here and say overlay on Quake? Now I have got managed APIs that are running and being rendered on top of this formerly native rendering surface. And all I had to do to make this work, or all rather Vertigo Software had to do to make this work, was recompile the Quake 2 application with the IGW technologies, and then add in the appropriate calls to this new managed radar feature that they've added. And it works, and the performance is great. It's about a 10 to 15% slowdown from the maximum optimization using our Whidbey compiler from native. So it'd be great if we could do this with a variety of other applications. But it requires understanding the way some of these technologies are built if you want to make sure that you can always construct a solution that will work appropriately. And that's the subject of this talk. We're going to dive down into the interop technologies and into the code generation technologies for our ref types and our CLS compliant features, see how the compiler generates these, and then we'll be able to better understand them for when we write our apps and want to migrate forward to using some of the WinFX APIs. My name is Scott Currie. I'm a program manager with the Microsoft Visual C++ product unit. I work on the back end of the compiler specifically. So that's the optimizer. Those are the JIT compilers. Those also covers managed code generation and the code generation that happens to support this interop technology. My email address is here if you have any questions about the talk that you don't get to ask, or you want to dive into some of these features for specific projects that you're working on, feel free to send me an email, and I'll try and be as responsive as I can given the heavy workload they give us at Microsoft. So the agenda for today, there's usually a pretty wide disparity among developers and how much they know about interop technologies. So we'll spend a few moments on the basics just to make sure that everybody is at the same level. From there, we'll move on to compiling C++ to MSIL, and specifically what some of the challenges are in getting your existing C++ code that uses native types to compile into MSIL and run on top of the .NET framework. We'll discuss the role of machine code, or the native code for x86, i64, or AMD 64, why you still want it in your images, and how we deal with having it present in those images. Next, we'll discuss compilation modes. We've added 2 new compilation modes for the Whidbey product that will increase programmer productivity and enable a wide variety of scenarios that were either not possible with the 2003 product or were very difficult to accomplish. The optimization section of the talk will discuss some of the optimizations that we're able to do on verifiable code and on non-verifiable code. So you'll see some of the things that the C++ compiler does to help out the JIT compiler and get you better performance than you may be able to realize using other .NET languages. Finally, we'll discuss MSIL linking, which is a great new feature. The link.exe tool, the C++ linker, in the Whidbey timeframe will be able to consume .NET modules produced by any .NET compiler. The result of that is that you can create a single file, multiple language assembly using the C++ tools. This is something that was never possible before without having to create some pretty terrible hacks that I'll discuss later on. and it enables a wide variety of cross-language solutions that previously required multiple file deployment. So let's start with the basics. There are two main CLR technologies that you need to understand in order to go forward with this talk. They're MSIL code and CLR data. Code and data, though they are related and they reference each other on top of the .NET frameworks, aren't 100% intertwined. Just because you have MSIL code doesn't mean you have to have CLR data, though you usually have to have MSIL code to have, if you do have CLR data. So MSIL code, it's a portable, stack-based representation. So it's just like one of these HP calculators that you might be used to using, or something that uses RPN notation. Pushes things onto a stack, pops off arguments, performs operations, and pushes the result back on. One of the main benefits of a stack-based representation is it's very easy to do the verification that's required for some of the very interesting security features of the .NET frameworks. All this MSIL code is compiled by the JIT compiler to native machine code, which then gets executed on your machine. Your CLR data is any data that resides on the garbage collected heap. By sitting on the garbage collected heap, you avoid a lot of problems such as memory leaks, a lot of bugs that tend to show up in software. By putting things on the garbage collected heap, you avoid this class of problems entirely. When you're on the GC heap and when you have CLR data, metadata encodes all of your type information. So very basic stuff here. But this leaves a question about C++. All this verifiability stuff with MSIL is great. I'm sure you've heard a lot about it. I'm sure you've heard about it with other managed code platforms. But with your C++ code, you're using pointers. And you're using them in ways that no verifier is going to be happy with. But that's the great thing about MSIL and the .NET frameworks, because it has first-class support for unverifiable instructions. So in addition to being able to do your verifiable data access through your metadata with your verifiable instructions, you can do pointer arithmetic. You can do indirect loads. You can do whatever you need to get access to the native heap and to compute where you need to be in statically laid out types. That's types that are laid out by the compiler. So let's have a brief demo of what some of these instructions look like, and that'll conclude our basics, and we'll start to drill down pretty deeply into how we wire up a lot of our technologies using these instructions. So here we just have one simple file. I've got a native struct that I've created. I call it int capital. It's got an int pointer here, which is a buffer, and then it's got this internal member, and the internal member is what I really want to get at. So since this type is compiler laid out, what I'm going to do is have a pointer to this int structure I, but I need to get at I plus, on a 32-bit platform, 4, which will be my pointer to internal. So I'll build this application, and then I've got a tool set up here. All I'm running is ILDASM. If people don't believe me, I can bring up the external tool definition. But ILDASM comes up on this particular exe. And I've got a couple of things in here, but right now we want to focus on main. So we've got our main implementation here, and the interesting part are these three lines. The first line does a load of the address of the local named I. That's our int I. The next loads a constant, 4, and the third adds that constant 4 to the address. I've just done pointer arithmetic here. Now at the top of my stack, I have I plus 4, which is a pointer to internal. I do an indirect load, and now I can store it to where it needs to go. So this is the way these unverifiable instructions work. Now, this runs. I can hit F5, and it'll execute. Press any key to continue. But if I try and run it through PE verify, I get all sorts of complaints. But that's okay. If we don't need verifiability, which a large number of client applications don't, then we're fine without having it, and we benefit much more from being able to bring our code forward in a usable way. So now that we've seen some of these basics, let's move forward to how we use these basic technologies in order to get C++ represented in MSIL. There are two different types that you can represent in C++. They're the CLR types. These are what in the 2003 time frame used to refer to as __GC or __ value types. They correspond directly to ref types and value types on the framework. We've also got native types, which were our types that we didn't have any modifications on. They were just classes or structs. Now, if you've got a CLR type, your type is represented fully in the metadata. You've got your full description with all the fields and all the members. The members of the type are implemented in MSIL. All the scope and visibility, so are they private, public, etc., that's all specified in the MSIL. The access to specific members of the type are all runtime enforced. They're compiler enforced as well, but at runtime, make sure that at runtime you're not doing anything bad with them. And as a result of some of these limitations, the optimizations are limited. And we'll discuss that later on when we talk more about optimizations, and specifically some of the limitations you can run into. All of your data is going to end up on the managed heap if you're using the CLR type. Your layout is almost always determined by the runtime. The only time it's not determined by the runtime is if you do explicit layout using attributes on your code. In order to get at your members, you always use named offsets. You don't do any pointer arithmetic at all. So let's drill down and do a demo and see, given some code, exactly how things get laid out. So I've got a few examples of different types that you can have in a C++ application. So I've got my .h file, my header. I've got using namespace system, just for some syntactic sugar there so I can avoid having to type a little bit more. I've got an enum here. This is a managed enum. I call it text num, which is very simple. 1, 2, 3 are the members. I've got an interface class. Interfaces are supported by the .NET Framework. I call it tree, and it exposes a public method count. I've got a value type. Now notice the new syntax. There's no underscores here. We have a new set of CLR language features in C++ that make the .NET programming experience much better. If you want to learn more about these features, you'll have to attend Herb Sutter's talk. I believe that's tomorrow. He discusses all of the new language features for targeting .NET with C++. He's going to drill down a little more into some of the more advanced language features and how we do code gen for them. But since I would have to discuss a lot more about the language in order to introduce those concepts, I'm just going to stick to the basics here for now on CLR types. If you want to learn a little bit more about that code generation, make sure to attend his talk. So I've got this value class using the new syntax. Notice here it's got a handle, which is, you can think of it a little bit like a pointer, though it's not. It's just a handle on the GC heap to a parent tree. And I've got these functions declared here. And since it implements tree, it also has to have this count method, which is exposed. I've got the same thing in a ref class. So instead of being stack allocated, like the value class is, the ref class will always be heap allocated. And again, I have a similar layout here. And in my CPP file, I just implement those methods that I defined. And I just instantiate members of each of these types. So if I go ahead and build this, of course it'll run. Doesn't produce any output. But what's more interesting is what it produces here in the ILDASM. We've got something that looks very structured here and very nice. I've got my ref tree, which is my ref type. It's got all its members fully described. It's got this integer, A. It's got this floating point value, B. It's got its parent class. It's got a constructor, and it's got the count method. I've got my value tree, which looks very much the same, except it's specifically here a value type, so it ends up on the stack. I've got my interface tree, which defines count, and I've got my text enum, and here are all the members there. So very, very nicely defined here. And if I double-click on any of these, I get the IL for it. And of course, I also have my IL for the main function. Things get a little messier once we move on to native types. Switchbox doesn't seem to be working here. Oh, there we go. For native types, we have a more difficult code generation situation. In order to make all of this work, we had to make it such that the types did not exist in the metadata. You would have often a reference to the type just for the purposes of referencing, but that type wasn't filled in, as you'll see in a moment, as they were for the CLR types. All of the methods are members of the module. They're not actually members of the type. So everything gets kind of promoted and pulled out, and they're on global scope. Also, since everything's globally scoped, that means it's all fully public. So access, like private, protected, and internal, all has to be enforced by the compiler because the runtime just sees everything as fully public. And since it's fully public, we get a side benefit. It's all very optimizable. We can run a lot of code through our optimizer and actually optimize the MSIL. And I'll show you an example of optimizing native types later on and how much power we actually have. All of your data resides on the native heap. And the way it's laid out on the native heap is the same way that the compiler would lay out that type if it were native and it were sitting on the native heap, if you hadn't compiled /CLR. You are doing pointer arithmetic to access your fields, so you're not getting verifiability. Since you're laying out your types this way, there are some limitations. Since you don't actually have the type fully represented in metadata, you can't do pound using. or a /add module in VB or C# in order to get at your data, in order to get at your types, because your data members won't be exposed. The only way to see these native types is by pound including the object's header file, and consequently, the only way to see them is through C++. Of course, that doesn't preclude you from writing a wrapper where you do a pound include, you see the native types, and you wrap them using managed types where you just expose out all the functionality. And that's actually a common strategy that people use for bringing some of their code forward. If you want to hear more about those particular strategies, I've got a talk on that on Wednesday, and I'll tell you a little bit more about that later on. You can access the member methods. They are members of the modules, not of the type, but you do have access to member methods through reflection. So if you really needed to, you could access those from other languages, but it is quite awkward. So I'll show you a demo of native types in action and what some of the code generation looks like. So here we have just two files, again, nativetypes.h and nativetypes.cpp. And I've done a bit more here because some of the code generation is different in different situations. So I've got everything I had before. So I've got an enum, textnum, 1, 2, 3. I've got a class tree. Now notice we don't make a distinction here between a value class and a ref class because there is no such distinction. In C++, native C++ rather, if you want to allocate something on the stack versus the heap, you just will either do a stack declaration without a new, or you'll do a heap declaration with a new and a pointer. So the classes are a little more versatile in that way. You've got some private members here. You've got some public methods. Notice these members here. And remember, we've got 4 of them, and we'll keep that in mind when we look at the ILDASM for this. I do a type def just to show you what happens when we end up in the MSIL. I've got a function pointer. I've got a couple of functions. And in my CPP file here, I've got a global array definition. I've got a pointer declaration here. I've got another pointer declaration, but this time it's initialized globally. I've got a static int. I assign e to the result of this goop function. I do a couple more declarations here, and then I fill in these method implementations. So let's take a look at the ILDASM and see how much messier it looks. So that's what it looks like when you do a CLR compile. And I'll go through these and explain exactly what they map to in the source code. So starting off with the first member, we have this A15 here. So this is just a global array, and the compiler has to set up a type that this global array references. So what it does is it just creates this name mangle type. It's an array type, and it has some name mangling after it. And that name mangling includes various pieces of information. The most important piece of information it includes is the size of that particular array. If I open this up, you just see some of the attributes that are necessary to implement this. There's no information except for the name mangling array type. The next thing I see is foo. So I did define my type foo here as a type def struct. It's foo. But when I actually look, it has a member bar, but here it has no members. All it has is room for bar. And the compiler has to figure out in its code generation where to stick the appropriate data. It's a similar thing for tree. We all saw the definition of tree. It had several members, but here we see no member data and also no member functions. A couple of other features here that are important. You see these initializer functions. These initializer functions are omitted to be called on CRT startup for these initializations. So we're initializing C to new. This happens up front as soon as the CRT loads. We're also initializing E to the result of goop. So we implement these particular functions here that will perform the necessary initializations. And it's just metadata for them so they can be called appropriately. We've got a couple of entry points here. And entry points will make a little more sense later on. But these are managed to manage entry points. So I've got a variety of functions that I've implemented here. For example, this tree constructor or this void pointer here. And these types correspond specifically to the types that are represented by those functions that get compiled. If I go down some more, I finally start to see some of the some familiar things. All of my globally defined variables, A, B, C, E, they all end up in the metadata. And they all have these RVA values. They're specified here by these Ds. They map directly onto RVA values associated with them. So they end up being process globals. They are omitted in the metadata just for description purposes. And the last interesting feature that I want to show down here is your functions. Now, I've got these functions here, such as the tree count function and the tree constructor function. Notice these aren't members of tree. They're global members, and we use name mangling to show that they are tree.count or tree.ctor. They've got the implementations in MSIL, but they're not nicely laid out as they are in the case of reference types. So moving back, we'll discuss the role of machine code, because so far everything we've seen is MSIL. And MSIL is very interesting, but there are some limitations and some reasons why you'd still want machine code in your image. The first major one is that you might have some performance-sensitive or very hand-tuned code. You spend a lot of time making that code very fast, and you don't want to just do a recompile onto a new platform, essentially, that has different performance rules and have to retune. You might be very happy with the performance you already have and want to keep it. Alternatively, you might have used some inline assembly, or you might have used some intrinsics that are CPU-specific and can't be compiled over to MSIL. And of course, perhaps most importantly, if you have exports to native applications, so you have native applications that don't know anything about the CLR, that want to call in to your image that you're compiling /CLR, you have to have something native in that image to call into. Because your caller doesn't know anything about the CLR, so you're the one who has to have the native code that knows about the CLR. So what's the solution? The solution is mixed images. There's no reason why we can't take this machine code and just stick it into our assemblies right alongside the managed code. And the reason for this is that our .NET assemblies are just portable executable files, PE files. They're the same representation that we use for native code. But we add some extra data to them. We add a CLR header, and we add data blocks which contain the metadata and the MSIL. So here's an image directly from the CLI spec that shows how this is laid out. You've got all your PE headers, you've got your CLI header, you've got your CLI data, which is just a big data block, which got the metadata, IL bodies, and the fix-ups, and then you've got all your native image sections. So you've still got a place for everything native in that image that you want to put there, and you've got an OS loader that knows how to load it. So the OS loader and the CLR loader just cooperate to get everything working. So I'll show a quick demo of exactly how this ends up getting emitted into your images. So I've got some machine code, which is emitted when I compile this file here. It's very simple. I've got the struct foo. It's got a member int bar. I just instantiate that, so here's some MSIL that's done to do that. But then I'm going to call into printf. So printf is a very native function, and I'm including stdio.h in order to get it. So I do a build, and the first thing I'm going to show you is the disassembly for the IL. Now, if you look at main, that gets implemented in MSIL. Here's the code for instantiating foo. And we've also got a call down here for calling into printf. Right there. But the problem is that we've got this function printf, which has to have some embedded native code there. It's linked into the image. Now, we can't show any native code here, but we know it's there, so we know it has to have a place. So if we run dump bin and we dump the headers, which I've just done through there, now I'm going to open it up, file.open. File. And here's the spit that came out of dump bin where I just dumped the headers and the CLR headers. I've got something, how many folks have taken a look at the output of dump bin before on a native image? Okay, a fair number of you. So a lot of this will look familiar. You've got your file header values. It tells you what machine you're running on. It tells you how many sections, some time date stamps. It's got some optional values. It's got your magic number for P32. It's got your data and code base numbers. It's got an entry point address. A variety of other things here. And then after all of your native code, after all of your native headers, rather, and after your section headers here, I've told it to emit the CLR header. So the CLR header is just right there. It tells the runtime version. There are some CLR-specific RVAs here. And it's got a managed entry point token. And it's also got an offset into the code. So this is just the spit from dump bin, and this is a good way of being able to tell, for example, if you've got an image and you want to know whether or not it's got any CLR-specific stuff in there, one very easy way to tell is just run dump bin /CLR header and see if you get a CLR header out. If you do, you've got a managed header in there. So that's how mixed images are put together from a very high-level perspective. We're going to talk about compilation modes, and through doing that, we're going to drill down to a lower-level perspective, how mixed images, pure images, and safe images get put together and wired up. So here we have our code and our data, as we looked at before as our basic technologies, and we've got two modes for each of these. We've got CLR and no CLR. So if you've got no CLR code, you're talking about machine code. This is x86, i64, AMD64 machine code. If you're talking about CLR code, you're talking about your MSIL code. If you've got no CLR data, this is your native data. It's residing on the native heap. These are your native types. If you've got CLR data, these are your CLR data and types, your ref types and your value types. So we all know the role of native code. It's machine code, it's native types. If anybody has used the Visual Studio 2002 or 2003 /CLR capability, you all know about /CLR in the mixed mode, which we'll dive into in a second. But first, how many people have used /CLR so far? So almost everybody. That's great. So interop fundamentals. How do we make that mixed stuff work? Well, the real magic here, and you may have heard before the interop technologies referred to as IJW. That's what we used to refer to them as internally, and that name kind of leaked out even though we never made it public. It stands for It Just Works. We're calling them the interop technologies now. So the magic of these interop technologies is that all global or native memory methods have both unmanaged and managed entry points. And this is extremely important because by having both of these entry points, every function that you've compiled /CLR that is a native, that was a native type can still be entered from any of your native code because it's got that unmanaged entry point, and it can be entered from any new managed code. So you've got that flexibility. One of these entry points is going to be your actual method implementation. The other is going to be a forwarding or transition thunk that just does the appropriate transition and then calls into the actual method implementation. Your method implementation is almost always MSIL. The only cases where it's not are when the compiler can't generate the MSIL because you've done inline assembly or you've done the CPU-specific intrinsic, as I mentioned before, or if you specifically say that you want machine code implementations for that particular function. And you do that with the pound pragma unmanaged pragma, which specifies for that particular code block that you're surrounding it with, you want that implementation to be all native code. So when you're actually doing the transition from the one entry point to the other, you have to do some work because .NET code and native code don't know how to talk to each other directly, especially on x86 because the calling conventions are different. The calling conventions for managed are actually use a reverse parameter order from native. So one thing that has to happen is you need to adjust the calling convention. You need to switch the order of any of the parameters. Type marshalling might also have to take place if you're trying to pass managed types to a function that expects a native type in a particular place or vice versa. Also, some adjustments occasionally have to be made to the garbage collector. So you've got two types of thunks that can make these transitions. The first one is called the IJW thunk or the interop thunk, where the compiler provides an implementation for the thunk, and you call into the method from that thunk through some offset or IAT jump. Managed p invokes, on the other hand, don't have a compiler-provided method implementation. The compiler just provides a declaration for these, and then which is a managed p invoke with complete metadata. Then the runtime handles all the interoperation. As far as cost goes, the IJW thunks tend to be a bit faster than the managed p invokes because the managed p invokes tend to have more information. Even if you don't have to do any marshalling, there still are marshalling checks that cost some time. There have been some figures quoted that it takes as little as 10 cycles to get one of these transitions done. I've personally been able to make that happen, but it required a ridiculously contrived test case. In the real world, you're looking at x86 more like 50 to 300 cycles to get a transition done. So they are expensive, and that's one thing you have to keep in mind when you're doing a migration path from your existing code to using some of the .NET APIs, and make sure that your managed to native interfaces aren't too chatty. And we'll discuss that a little bit more later on, and also in the other talk that I'll be having on Wednesday. So here's just a quick illustration of what these p invokes look like to make sure it's all clear. For the managed p invoke case, you've got your managed caller. It calls into this managed p invoke, which was specified by the compiler, but it gets implemented and generated by the runtime. And then this calls directly into the native target. Everything orange here, by the way, is managed. Everything native you're executing, everything native that's being executed is in green. The IGW thunk, you start off with your managed caller. You have your runtime generated managed p invoke, which is just a very thin shim that does some necessary transitions. And then you go into your compiler generated IGW thunk, which is going to be a native code, and then you call into your native target. So when is one used versus the other? Well, in 2003 in Whidbey, if you're doing the /CLR compile, whenever you're calling intra-assembly, IGW thunks are always used. So if you've got a native implementation here and you've got a managed caller and you try to call into your native target and you're in the same assembly, you're always going to use an IGW thunk. You're not going to have one of these proper p invokes with the full implementation map. If you're doing inter-assembly, it can go either way. If you're doing something like a pound include of stdio.h and calling printf, you're going to use an IGW thunk because that's been implicitly specified by the user without having any explicit implementation. That's really all the compiler can do for the mixed case. If you explicitly specify it, for example, by using the DLL import attribute, you can get the p invokes for cross-assembly. So if you do a DLL import on your printf, you'll end up using the managed p invoke, which is actually a little slower. So here's a demo, and I'm actually going to drill down here into managed versus native code in the image and actually take a look at how you can tear out the managed and native code, how the native code gets generated, when it gets generated. So we start off, we just got one simple file here. In fact, it's the same one that you saw before. We've got the struct foo. It's got a member int bar. We've got main, which instantiates foo, prints hello world, and then returns. So I build it. I go up to tools here. We can take a quick look at ILDASM and see here that we get all of our MSIL for main, right? But we do still have this problem where printf has this embedded native assembly. I want to see that native assembly, and I want to see how some of these things are wired up. So I can do that by first just compiling my image by using, as an output file, assembly listing. So when I do that, I've got my assembly listing. It's been generated in my directory. So I'm just going to open it up here with a file.open file. It's in the debug directory. And I've got this mixed.asm. So here's the assembly listing that was generated by the compiler. I start off with the global data with local declarations. Here's the implementation for main. And you'll notice that as you go down that this is MSIL. And we know that our main implementation is MSIL. Our compiler, when we do assembly listings, if you've got a mixed image, will emit the MSIL alongside the native code. So here's all MSIL for the MSIL implementation. And as we continue going down here, we'll see that we have a couple of entry points here that are native that use our native code. So we can see a couple of these thunks here in action, and if you drill down, you can actually kind of trace what they do by jumping between the entry points. And I'd suggest that as an exercise at some point, that you just kind of go through and see what's happening, because it's kind of important to understand. And if you understand how these thunks jump around, you'll have a lot more power in reasoning about how the interop technologies work and where some of your performance trade-offs might lie. But what I'm really interested in here is the call to printf. So here I've got this call to printf, and it just calls this name-mangled printf. Now here's the interesting thing. When I have the compiler look at this file, and it sees the declaration for printf in stdio.h, and it sees printf, we all here know that printf is a CRT function, and it's implemented as native. It doesn't have a managed version. It doesn't have a managed entry point. But the compiler doesn't see anything special at all about stdio.h. It's just another header file. It could very easily be a header file that you, the user, implemented. And it could very well map onto an object file that you, the user, have compiled /CLR. So what it has to assume off the bat is that it could be either way. So what it does is it says, well, it might be managed. If it is managed, I definitely want to call into the managed entry point. So I'm not going to cause myself some performance problems here by choosing the native entry point. So I'll leave my door open here. And I'll just refer to this symbol. But then, when the linker sees this, and sees that the method implementation is actually in native, something has to happen. Because as we just said before, you can't call directly from MSIL into native. And that's why if you actually do a dump bin on the assembly, which I've just done, and then you open that file, I've called it mix.postlink, you see quite a bit of x86 assembly code here that wasn't there before. Now, some of this gets linked in by the CRT, but other parts of it, if I keep my eye on these labels, are jump thunks for printf. Let me just find printf. So here's sprintf, and it's got its native implementation here. But this isn't nearly long enough to actually be sprintf. What it is it's a thunk that the linker generates in order to call into sprintf appropriately. So what's actually happening here is the linker technically is generating code, which, if you're a linker purist, shouldn't happen. In fact, we've got some linker purists at Microsoft, and they fought long and hard over this one. The thunks, though, aren't really code generation. They're just static data that's getting emitted into the image by the linker. So it's not too bad. But it definitely is happening there, and it's something that you need to understand. Just by looking at assembly listings out of the compiler, you're not getting the whole story, because the compiler doesn't know the whole story. To get the whole story, you either have to step through in a debugger that gives you an assembly listing, and you can step through all the assembly instructions. That's the native assembly. Or you have to do a dump bin out of your exe. So this pretty much shows you everything you need to know to take a mixed image and tear it apart. You can get the managed parts out. You can get the native parts out. I showed you in the last demo how to look at the header. And there's also another tool, which I'm not going to demo here, called metainfo. I've already showed you a look at the metadata through ILDASM. If you use metainfo.exe, you can get a much more detailed look at the metadata tables. It's not particularly interesting unless you know a good bit about metadata, and of course if you're using managed types. So going back, we've now drilled down a little bit into our mixed code generation. We've added a new type of code generation for Whidbey, and that's called pure C++. So there's some issues with mixed images that motivate having pure. First, if you've got these native image constructs, you can have all sorts of issues in some scenarios that are going to become more important over time. The first kind of very important thing is that mixed images aren't CLI compliant. Now, the CLI spec does have some notes about mixed images and what you have to do to make them work, and has some suggestions for implementing the types of VT fix-ups that are required, as an example. But they're just notes. CLI implementers aren't required to implement those notes in order to be compliant. So you don't have the CLI compliance. Also, the existence of a native entry point wreaks havoc on a lot of tools, especially if you're using reflection. Consider the problem of reflection. In order for reflection to work properly the way that it's been designed, it doesn't just inspect the metadata tables and give you your answer back. What it actually does is load the assembly, execute the assembly, and once the assembly is running and all the initialization has happened, it can then start calling into APIs that will examine metadata in the running image. Now, if I've got a native entry point, has anyone ever tried to call load library on an exe? Doesn't work too well, right? Especially if, for one thing, you've got image rebasing problems, which you can get around. But if you've got the CRT running, at the end of your main function, you're calling process exit, right? So you've got two options if you're the CLR and you want to try and reflect on something with a native entry point that's an exe. First thing you can do is just call the thing, and it takes over your process and you die when it's done. Or you can not call the thing, and you don't get any of your initialization done properly. So it's a lose-lose scenario, and it doesn't work properly. There are a variety of scenarios where these reflection capabilities are necessary. For example, click once deployment, which is the .NET deployment model that we're introducing in Whidbey. Another example are any tools that use reflection. So if you're using something like a document generator, which will go through your metadata and pull out all of your type definitions, that won't work on something with a native entry point. Also, you can run into transition penalties. Since you've got this native code in there and you're calling in the managed code, or vice versa, there are situations where you can call into native code when you actually don't have to. If you want to learn more about that, that'll be in my next talk, leveraging C++ with existing C++ code with .NET. And that is a talk that just focuses more on some of the practical aspects and specifically some of these performance aspects. Also, if you've got static data, you've got some issues with sharing your data between app domains if it's globally scoped, and that's a problem. So the solution is pure MSIL. So all you do, if it's going to be pure MSIL, you cut out everything native. And what you get is something that's CLI compliant. You get these compelling scenarios, for example, click once. Another thing that uses reflection is the form designers. It reflects on an assembly to render a control. And if you happen to have that control defined in an exe, it won't work with the form designer unless it's pure. So pretty much anything that uses reflection, you get to win. You've also got these potential performance wins by perhaps eliminating some of those transitions. But keep in mind that pure code is not necessarily verifiable. Just because it's CLI compliant doesn't mean that it doesn't use those instructions that we discussed in the first demo that do pointer arithmetic and indirect loads off of those pointer arithmetics. So what about interrupt? If it's pure, how are we calling into these functions like printf? Have we just crippled you? Well, the answer is no. And the reason for that is for the pure scenario, we've introduced a new feature in the linker where the linker can take the IJW thunks and construct from them one of these managed p invokes by filling in the appropriate metadata. So instead of actually, to get pure working, having to do an explicit DLL import on MSVCRT and get your printf here, all you have to do is your #include_stdio.h, and it all works pure. So you might be saying, great, they're CLI compliant, so that means they're portable, right? Well, not quite. What it means is that they're portable among any compliant CLI implementations on the same platform. But they're not portable, they're not necessarily portable among platforms. And there are a couple of reasons for this. One of the reasons is CRT initialization. The initialization that happens for x86 versus AMD 64 or i64 are completely different. If we wanted to try and get those to be cross-platform, we'd essentially have to embed the CRT initializations for every platform we knew about into the image and just select the appropriate one at runtime. And I'm sure nobody's interested in that type of code bloat. Also, for native types, your data is statically laid out. It's laid out by the compiler. And on different platforms, you often have different pointer sizes. Right? So if I'm on a 64-bit platform and I've got this pointer and a struct followed by the data I actually want, am I adding 4 to get to that, or am I adding 8? That's a problem that the compiler can't get around. Now, theoretically, we could just pad everything out to the maximum. So we're going to assume it's going to be 64-bit. We're going to assume worst alignment scenario. But then a new platform comes out and it's got new alignment restrictions, and we have to start all over from scratch. So it's kind of a difficult situation to make these portable, and it's not something that we're pursuing for Whidbey or really in the foreseeable future. So here's a demo of pure code. Open up my solution here, and we're going to see something that looks very familiar. We've got the same thing as before with the struct int and int pointer to a buffer, and we've got this main function, very similar to what we had before. But now we add 2 additional things just to demonstrate how good the compiler is about telling you what you can't do in pure. So I've got a seedecl function, which means by definition that it's got to have a native entry point. And I've also got an asm block in here that happens to be empty, just for demonstration purposes. Now in this version of the IDE, we don't have the really nice support yet for specifying CLR pure versus CLR safe. I don't know if you can see it here, but I just did /CLR:pure. If you want to go home and use the DVDs that are in your bag, this works, by the way. You can do /CLR:pure and it will work. So I do my build, and I get a couple of errors here. The first one says, foo, invalid calling convention seedecl for a function compiled with /CLR:pure. So I can't use the seedecl calling convention. Well, for expediency, let's just say I didn't need it and I didn't know what I was doing and I put it in there anyway. So I'll get rid of it. Let's try and rebuild again. And it says, __asm causes native code generation for the function in foo. Obviously, that's not allowed in pure. So since it's not actually doing anything, let me just eliminate it. In the real world, I would have re-implemented that asm block if I actually wanted to go pure with this. And these other 2 warnings just say that they can't compile the unmanaged function with CLR pure as a result of that asm block. So if I recompile now, I get a successful build. Now remember all that text we were seeing in that disassembly that we generated out of dump bin for the mixed assembly. A lot of that was CRT initialization. And it was all native and it didn't show up in ILDASM. But now when we open up ILDASM, look what we have here. We've got managed CRT startup and shutdown. These are all the things that were previously implemented in native are now implemented and managed. Now this really messes up the global namespace. In this particular version of the compiler, it's emitting them into the global namespace. For Whidbey, when we actually ship it, they're going to be implemented in a separate namespace so it won't clutter things up so much. But we've got some nice things here, like when I go down to printf and I double click, now I've got, instead of native code embedded, I've got my actual full pinvoke impl with the implementation map filled out. So everything here is pure. But keep in mind, when I do a p-verify, I get errors because it is not verifiable. And let me just give you one other quick demo, and this also demonstrates another nice feature we have of being able to finally very easily cross-target to our 64-bit platforms. All I do is change to Win64, AMD64, and now I'm ready to compile for AMD64 using the cross tools. I've just done the build. It's linking. It's successful. Now, if I do an ILDASM here, and I take a look at main, where previously I was doing my add 4 to the pointer, now I'm doing add 8. Obviously not compatible. Just a very brief demonstration that that actually is the case. So that's pure in a nutshell. Since it's pure, we get to do all those interesting reflection scenarios. But of course, pure only buys us a little bit. The real holy grail for the .NET developers, especially if you're looking at things like mobile deployment or writing scripts for Yukon, is being able to do verifiable. And that's the third mode that we have for CLR compilations. We call it CLR safe in Whidbey. This enables all of your low trust scenarios. If you're trying to run something over the web, if you're trying to run something over file share, if you're writing an animal for terrarium, you definitely need it to be verifiable. If you're writing a script for Yukon, you need it to be verifiable. It checks for a couple of things. One thing it does is it makes sure that you're not using any native types. Whenever you're using native types, you're doing pointer arithmetic, and that's not verifiable. This makes it potentially more portable. Since you're not going to be using C or T initialization, because none of that stuff is verifiable, and you're not using native types, those are the two big problems we run into. You still can get yourself into trouble from a portability perspective, but it's the same trouble you can get yourself into with any other .NET language. For example, C#. For example, you can get yourself into trouble with endianness and bit shifts if you happen to be running on a platform which is little endian versus big endian, depending on where you develop. How does it work? It just says any non-verifiable constructs, you're not allowed to have them. Compiler enforced, and you actually get some very good warning and error messages about that, which I'll show you here in the next demo. So here is the same thing before that we saw. I got rid of that other function that didn't really do anything. I've got the struct int in here. Now I've also got this managed tree class. It's very similar to the one we saw early on for the CLR type generation. It's a ref class, not too much going on there. And what I do is I instantiate an int, I assign its internal member to 0, and I create a new root. By the way, for folks who are used to compiling with the /CLR and trying to create managed types, we now have, instead of using 0 or null, we actually have a keyword for that null pointer. And this is really just the tip of the iceberg on the new language features, by the way. There are actually a large number of very interesting language features. I highly encourage you to go to Herb Sutter's talk to learn more about those. But when I compile this, I've got a problem. And I get some error messages down here, and they're very informative. First one says, int star, this type is not verifiable. Can't imagine a better error message than that. For now, all I'm going to do is convert this into an int handle. That might not be the best solution for a real application, but for expediency, that's what I'll do. The next one says int internal. Accessing this member of unmanaged class int yields unverifiable code. Well, we know why, because we're statically laying stuff out and doing pointer arithmetic. So let's just turn this into a managed type by adding value to the front of it. Now when I rebuild, everything builds successfully. If I then take this image and run it through p-verify, all classes and methods in safe.exe verified successfully. And of course, it runs. Now, one thing that you should notice here, if I run ILDASM on this, I, of course, am going to get all this nice output, because since I'm using all CLR types, I'm getting all the full descriptions in the metadata. So that pretty much covers safe. Has anyone actually tried to get a verifiable image out of the 2003 tool set? Raise your hand. No? Nobody? Good. It was probably one of the most painful user models that has come out of the product unit in a long time. Next, we'll talk about optimization. So optimization for the native code portions of a mixed image We've got some great improvements over 2003. We've done some tuning. If you're interested in just native code generation for non-mixed images, by the way, I highly recommend advanced code generation at 4:45 p.m. today. One of my colleagues, Hangsu Gatlin, will be giving that talk, assuming that he's not still stuck in an airport. MSIL for native types, we have several improvements over 2003. We were optimizing in 2003, but now we're doing a lot more. In Whidbey, we're doing pretty much every optimization we do for native, but we use different tunings because there are really different performance trade-offs for the .NET framework than there are for most machines that we deal with on a regular basis. And MSIL for managed types, we're optimizing them for the first time in Whidbey, really, and we're doing quite a bit. We're doing inlining, we're doing expression optimization, we're doing some loop optimizations, just as examples. So let's drill in and take a look at some of the issues you run into when you're working with GC types. Now, this just happens to be the old syntax. If I have this accessor method, which just returns this hidden, right? If I'm not inlining, I can have this main implementation, which just calls into type accessor, and then accessor will run itself, and I've just had to pay the penalty of a function call when I really don't have to. In native, I just inline that, and it'd be very simple. But what happens if I try and do the inlining in managed? Then I'm trying to do a load field of this type hidden up here. But hidden has private visibility. And I'm outside of the class type when I'm trying to do it. And this comes down to not even an issue of verifiability. If the CLR sees a construct like this, where you're trying to access something that's not visible to you, it's invalid IL. The CLR won't even run it, whether security is turned on or not. Major problem that we have for trying to do a lot of these optimizations. So what are some of the solutions? One of the things we're doing in Whidbey is analyzing for legal inlining opportunities. We do things like inspecting visibility, inspecting security boundaries, and inspecting attributes, and making sure that we're not running afoul of anything that the CLR thinks is important. Also, we're trying to relax those restrictions above wherever we can. And we're doing that by trying to do things like visibility promotion, where if we happen to know statically that you don't know, that you don't need any greater visibility, for example, if something isn't exposed publicly, it's only used internally with the assembly, we can actually promote it up to internal accessibility from the perspective of the runtime, and then from this perspective of the tool set, it just does all the enforcing in the source code, and that actually works pretty well. We haven't actually decided whether or not we're going to do that yet in Whidbey. In fact, there's a good chance we won't, but it certainly is one potential solution for that. What happens if we actually relax some of those restrictions and say, now we're not dealing with our managed types where we've got all this metadata that restricts us. Instead, we're just doing array accesses on native arrays, and we're compiling this to MSIL code. Well, if we're iterating over an array and initializing it, there are two ways you could conceive of writing this. The first way is the simple way. I start off at index 0, and I go up to the max index, and I just set it to 0 every single time. The second way, and keep in mind what this is actually doing, every single time you do an iteration here, it takes your index, has to multiply it by 4 since we're dealing with an int here, and then add it to the base offset and do your assignment that way. So you're doing at least one multiplication on every iteration. The smarter way to write it is compute what your end pointer is supposed to be. Start off with your pointer and just increment your pointer every single time by 4. So every iteration you're doing only one addition, not one multiplication, and you only do one multiplication up front. Turns out that when you're writing native code, our optimizer is smart enough to do this for you. You write the top, you get the bottom. There's nothing stopping us from doing the same thing in MSIL, and that's exactly what we do. Instead of having this nasty MSIL, which has this assembly inside the loop, this multiply instruction inside the loop body, in addition to a bunch of adds, we get a loop body that looks like this, which is just adding the appropriate amount to the pointer each time and does a pointer compare at the end. So all these optimizations you still get, and we're doing a lot of these, and that's one of the reasons why we're getting really good performance out of our CLR code generation on native types. Because wherever the JIT isn't able to do the optimizations that we know are necessary, since we know what the JIT's doing, we can supplement ourselves on the static side in the compiler. So the last thing I want to discuss is MSIL linking, and this is a really great feature. Blink.exe can now consume .NET modules. So whereas previously, if you wanted to have multiple languages in the same assembly, you had two options. The first option was you compile them all to different .NET modules, and you use alink.exe to put an assembly manifest into one of them, and then you ship all the .NET modules along with whatever assembly that you have that contains the manifest. The other way you could have done it is to make sure that everything you do is CLI compliant, which means you're not using any C++ essentially. You do an IL-DASM of all of it, dump out the ASM, concatenate it all into one big file using text processing, and then IL-ASM it again using IL round tripping. Terrible hack, not very convenient, and also doesn't permit you to have any sort of dependencies among those .NET modules in any real meaningful way. But now you can do that all by using a tool, creating your .NET modules, linking the .NET modules alongside with objects together, having dependencies among them, and you don't have to do any MSIL round tripping. So the linker can now consume native C++ object files, mixed C++ object files, pure C++ object files, safe C++ object files, .NET modules with C#, VB, or other language variety, and both pure and safe C++ .NET modules. So it's consuming quite a bit of stuff. Another thing that the linker team wasn't very happy about. So let's have a demo of MSIL linking in action. So we have a bunch of different files here. And this is all in one C++ project, by the way. The first thing I start out with is a VB file. Now notice I've got the VB text editor here. And I don't know why anyone would want to write code that looks quite like this, but there's a public class attendee, and there's a name and an email, and I've got a constructor there that just initializes them. Now I've got my mixed OBJ here, which defines this managed class party. So it's got a bunch of attendees that were defined, and the attendees, by the way, are implemented in the VB.NET module. And I can add as many attendees as I want. And then I've got this function called numTableConfigs. And essentially all that does is a combination. I tell it how big my table is, and it tells me how many different ways I could take members of my party and sit them at the table. And I just have this subset count function which performs the combination calculation to figure that out, to figure out how many subsets there are in a given group. And then I've got my C# function, which is implemented in this main class. It's just main. All it does is it says, let's read out the arguments that you've given me, and you're going to give me a name separated by email, and I'm going to add that to my attendee list, and at the end I'm going to tell you the different ways to sit them down. So I've got my party here, and I go to my properties and debug just to show you what I'm adding here. So my command line arguments, I'm going to have myself, Scott. I'm going to have Jeff Cox. I think he's in the back of the room there. I'm also going to have Bill and Steve over for dinner. So we do a compilation here. Now what's happened is I'm actually using the VB compiler is defined by this tool file. This is a great new IDE feature. If you want to learn more about it, since we're running short on time, go by the Visual C++ booth and we can show you how you define tool files and use them. But now this is just like an inference rule. Based on having the .vb extension, I'm going to run this command on it and produce the appropriate .NET modules. Same thing for C#. And then all I have to do in my linker is add those guys as new inputs. Now keep in mind here that this is a v-1 interface for this. We're going to have a much nicer interface by the time we ship. But right now, you can take the CDs in your backpack and use this functionality by just either plugging it in this way or by using the command line. So now that I've got this built, all I have to do is a quick run. And it tells me there are 6 ways to sit 4 people in groups of 2. If you look at the IL-DASM, just to make sure I'm not cheating here, we've got attendee, which was defined in VB, party, which was defined in C++, subset count, which was defined in native C++, and we see we've got embedded native code there, and main class, which was implemented in C#, all in one file, all working together. The way you define interdependencies between these, if you've got your C++, well, we all know how to do that. We use a pound using on the VB.NET module. If you're using your C# or VB and want to create a dependence on your C++, all you do is a /add module on the object file. The object file contains a metadata header, just like a .NET module, so it works the same way as far as the compiler is concerned. That's the C# compiler. So that's MSIL linking in a nutshell. This is something that's going to be used extensively within Microsoft, by the way. So in summary, by having these mixed code and all this framework that we've set up for you, you can gradually migrate to WinFX. You don't have to rewrite all your code in C#. Anyone who tells you how to do that, doesn't know about these technologies. But you have to be careful about some of your transition penalties if you're doing interop in points that aren't really optimal from a performance perspective. By having pure, you can go with a bunch of tools-based scenarios that weren't possible before. Safe is now really easy to generate. We're doing more optimization than we ever were before, and that'll get you anywhere between a couple of percent all the way up to, we've seen 25, 30% on some applications where the JIT was missing a really important optimization, mostly due to time constraints. And of course, we've got MSIL linking, which is a great new feature that improves the multi-language assembly story. In fact, if you want to go to the Visual C++ booth later on, I've got a demo, which we don't have enough time to show here, of a Rubik's Cube that's being rendered in DirectX 9, spinning around all over the place and solving itself as it goes, and it's implemented in 8 different languages, all linked together into one assembly. So additional resources. If you like this talk, definitely go to TLS 311. TLS 311, I'll be giving that talk, is going to take a lot of these concepts from the practical side. How do you actually do the interop? What are the trade-offs between different interop mechanisms? How much do they cost? How do you deal with app domain issues that we're more and more likely to run into as more and more applications start to use app domains and do CLR hosting? If you want to hear more about what we're doing for native code, go to Advanced Code Generation, TLS 400. That's today, room 408 A and B at 4:45 p.m. Send me lots of feedback, srcurrie@microsoft.com. Apparently there's this vswish@microsoft.com as well, but you're probably better off sending it directly to me. We've got public news groups that Microsoft employees are on all the time. If you're not looking at them, you definitely should. Microsoft.public.vc, and there are a few under there, and Microsoft.public.net.languages.vc, and there are a few under there. We've got a great hands-on lab here at the PDC where you can play with MSIL linking, verifiable code generation, pure code generation, Pogo, which is one of our native features, OpenMP, 64-bit code generation, pretty much everything we've got at the conference. We've got the Ask the Expert session. That's tomorrow night. I'll be there. And we've got the Visual C++ product booth. Also, don't forget the TLS language track lounge that they have upstairs. So that's the talk. We've got some time for questions. If anyone has a question, please step up to the microphone. And for anybody who's taking off right now, if you have any questions for me, you can find me for most of the rest of the day either in the language track lounge or at the Visual C++ booth. Question?
Yeah, I have a question about the calling of the native thunks. I think that if you call a function through a pointer, it's always calling the native thunk, isn't it?
If you call a what now?
If you're calling a function through a function pointer.
If you're calling a function through a function pointer in mixed code, you're always going to use the native entry point. And it will actually be implemented in MSIL, but you'll use the native entry point to do the call. Now, the reason for that is the time when you do the function reference, you have to choose one or the other. It's got to be managed or native. It can't be both. For compatibility, we always choose native. So what we do is have a managed caller calls in through that native entry point, which is just the thunk, which goes right back into the managed implementation. So that ends up being what's called the double P invoke problem, where you're paying for 2 P invokes where you should be able to do a direct call. In Whidbey, we've actually got some solutions for that. I'm going to go into pretty deep detail on what those solutions are in TLS 311.
Is this model also used for every call on a vtable pointer?
Vtables work the same way. You've got one vtable slot. You've got to choose one or the other, managed or native. For compatibility, we choose native. But again, we've got some solutions in Whidbey. One of the solutions is we can intercept the double P invoke before it happens and avoid it. Other solutions include language-level solutions where you can either compile CLR pure, and when you're compiling pure, you're saying no native code, hence no native entry point, hence I'm safe to fill in the managed entry point in the vtable or when doing my function reference. Or you can put a new keyword called CLR call on individual functions that you want to specify as having this managed entry point in order to avoid the interop penalty. So there are a variety of options. We've actually got 4 or 5 different things you can do to get around it. If you'd like to learn more, come to TLS 311.
Thanks.
Thank you.
When you produce pure code, you basically create similar to p-invoke signatures. Now that's not trivial in general. I don't know. I'm not sure it's even possible to do it for every possible call because you don't know whether its parameters are in, out, structures. Is that solved? Is that how would you know whether parameters? Let's say I have a pointer. You don't even know if it's in or out. Or
you don't have to know if it's in or out if you're talking about managed. If you're talking about native functions. All you're doing is passing around memory addresses. So just because you're doing your pinvoke implementation, you're filling in the implementation map, doesn't mean that you're specifying how to do the marshalling automatically, right? Because the way that you're consuming these functions is by doing a pound include of, for example, stdio.h. Stdio.h contains your function signature in there, which has got all of your native types. So when you both declare it and when you consume it, you're using native types, so you're just passing around pointers. So you don't actually have to do any marshalling in order to get that to work. All we're filling into the implementation map is a DLL, which the linker discovers on name resolution, and a function name, which is appropriately mangled.
So what about marshalling?
If you want to do marshalling, there are two options. One of them is to do a DLL import, and there, if you want to have marshalling actually done for you in some sort of non-trivial way, you have to specify it with a custom marshaller. Or you've got the other techniques that include COM interop and some of the managed C++ wrapper functionality.
So by default, compiler assumes default marshalling.
If you do a DLL import and you don't specify any special marshalling stuff.
No, you do include, let's say printf. Let's say printf is not a trivial function. Let's say, I don't know, format message or something, right? So there is some marshalling. You should really call local free instead of default marshal or something like this. So by default, if you just use that function, CLR assumes certain types of certain marshalling between native code and whatever, in the case in managed code.
It doesn't have, if you're using your native declaration in your native implement in your native call, using the same signatures, it doesn't have to do any marshalling. The worst, there still are going to be transitions. And for example, if you're passing something by value, you're still going to do a copy instruction, but you don't actually have to do any marshalling. You're just passing around native data types. After the talk, if you want to talk to me, we can actually go through a couple of examples and show how that works. Yes?
Yes. Right now, with the 2003 and before, we have a lot of wrappers, and those all get generated metadata into the assembly, which causes occasional name conflicts and confusion, particularly more the VB compiler, I think, than using from C#. But we've seen things where names that we didn't generate, it seems to be types that are auto-generated by the compiler, show up in the metadata, and we can't do anything about them other than change all our internal names.
We realize that's a problem. We're going to be solving that by using namespaces more aggressively. And also, as time goes on, we're going to work harder at being able to actually fill out the metadata better for some of the native types, which should avoid most of those problems. So in Whidbey, most of those problems will go away for you. Maybe not 100% of them. In post-Whidbey, probably all of them will be gone.
Hi. What are my options for exposing managed entry points as unmanaged callbacks?
For managed entry points, you have, it pretty much just works. If you've got an export in there and you've got a managed implementation there, you can use those managed entry points as long as you've got something that understands it. So if you've got C++, for example, calling in through a managed export, all you have to do is say that this function is an export, and you've got the call through. If you've got anything that's a managed type, all it has to be is a managed type that's public outside of the assembly, and then any CLS compliant language can take a look at that.
No, I was referring more, I think more of unmanaged code calling back into my managed code, particularly if I'm compiled with /CLR safe. How does that, does the linker then emit the relevant function?
So for the managed code calling back into the unmanaged code.
Unmanaged code calling, it's like, well, classic example, enumerating fonts. Say I want to write something which handles that enumeration, but I need to pass its entry point out to the Windows API. How do I go about what's the story for doing that?
I don't think I heard the whole question. Are you talking about using callbacks?
Yes.
Okay, so callbacks are a little more complicated than we can probably cover talking across a room of 200 people. So come see me afterwards, and anybody else is interested, just cluster around.
Thanks.
Any other questions? Well, thanks everyone for coming out. Hope you enjoyed the talk.